So I've been learning Rust for about 4 months now, and I've completed another project I want to report about. This time it actually resembles a real software project and can even be considered marginally useful. Yet again, this was a pretty simple project, but the learning was tremendous. Now I have a much better understanding of the Rust ecosystem, idioms, design patterns, and some essential traits. There's still a long way ahead, but now Rust doesn't feel as scary as it was at the very beginning of my journey. So what's the project, you may ask? This time I was working on creating a basic synthesizer. It takes notes from the standard input or MIDI commands from a file and generates some sounds based on this input. It doesn't use any libraries to actually play the sound. It just generates some PCM data and spits it out directly to the standard output, which can then be piped to a program like FFplay from the FFmpeg suite to make it audible. Let me show it in action, and then I'll talk a bit about how it works and the decisions I made to implement it. Protect your ears. The theory behind synthesizers is vast. I'm not well versed in it, so I'm only using the very basics that I know well enough. To synthesize a basic sound, the first thing we need is an oscillator, something that will generate a periodic signal with a given frequency. These are some frequently used patterns for such signals. Square, which sounds like this. Triangle. Sawtooth. Sine. Also noise, which can be very useful, although it doesn't sound like it from a basic example. As you can see, each oscillator has a waveform pattern that repeats at a given frequency. In terms of wave physics, each pattern like this is called a period. So if you want an oscillator with a frequency of 440 Hz, which is the frequency of the note A on the fourth octave, it means that each period of the wave must last exactly 1/440th of a second. In real life, sounds also usually change their properties over time, notably the volume. Something like a string stroke on a guitar produces a sound that can be loud and sharp at the beginning and gets quieter until becoming completely silent. To simulate this, synthesizers use another important concept known as envelope. An envelope is a set of rules describing the dynamics of the sound volume through time. Envelope usually describes such parameters as attack time, the time it takes for the sound to achieve full volume from complete silence after it's activated. It can be very brief, which makes for a sharp and assertive introduction of a note, or it can be longer for a more gentle and smooth introduction. Decay time. After the initial burst of energy, a sound can settle down a little to reach its normal volume. Sustain volume. Some musical instruments allow a played note to be held. Think of an organ, for example. While a key is pressed, the sound keeps playing on and on until it's released. This parameter determines the volume of the sound in this state. Release time. Continuing the analogy with an organ or a piano, when a key is released, it takes some time for the sound to completely fade into silence. This parameter describes how long that should take. To implement a very basic synthesizer, we need to combine these two components: signal from an oscillator and change its volume over time using the rules described in the envelope, to make it sound somewhat like a real musical instrument and not just a stream of beeps on blobs. Now let me show you the code I've written to implement this. Starting from the oscillators. In my implementation, an oscillator is a struct holding the frequency parameter, waveform, and keeping track of the time it's being played. Wave is a trait that requires each implementation to have a for method that returns the amplitude of the signal for the period given as the argument. The period must be a floating point value between 0 and 1. 0 is the start of the period and 1 is its end. The advance method in the oscillator is used to advance the time the oscillator is active, calculate the period of the wave from it and the frequency, and request a sample from the wave function. The synth struct is used to synthesize a sound using an oscillator and envelope configuration. Basically, it's just a small finite state machine that calculates the volume of the sound based on the current state of the envelope and multiplies it by the sample generated by the oscillator. Now let me show you the flow of the program from the very beginning. First, we parse the command line interface arguments using the clap crate, which is just magical and super easy to use. Then, if a MIDI file path is given in the arguments, we'll just go ahead and play it using the MIDI player struct. There's actually no good reason to wrap this player functionality in a struct like this, but my OOP mindset is still pretty strong, I guess. If no file is given, the program will read the standard input line by line, parse them, and play notes written in each line. Almost like classic music trackers do, but in a very basic form. But let's have a look at the MIDI player implementation, as it's more interesting in my opinion. I use the MIDI crate to parse MIDI files. MIDI files contain sequences of MIDI events. Each event knows how much time has passed since the previous one. All I do in this parsing routine is collect these events in a more convenient structure and convert the timing to seconds to make the calculations easier while playing. We are only interested in note on and note off events that signify when a particular note should start or end playing. Playing the music is a bit complicated. Essentially, we are running an infinite loop here. Every iteration of this loop must produce an audio sample that will be written into the standard output. As time passes, we pick events from the queue and create or stop synthesizers depending on the event. We know the sample rate from the command line configuration, and thus know that with each iteration of the loop, we will advance each synthesizer by exactly 1 over the sample rate seconds. There can be multiple synthesizers active simultaneously. To mix them, we just calculate the average value of each playing synthesizer. If there are no more running synthesizers and no more events in the queue, then the song is over, and we can break the loop, which will also terminate the program. Let's hear this atrocity once again, but this time let's use some other waveform just for a change. Thank you for watching, and I'll see you in the next video.